All right, welcome back to the deep dive. Today we are jumping into what feels like a pretty major architectural shift in AI safety research.
A huge one.
We're talking about OpenAI's new Circuit Sparsity toolkit, and our mission here is really to get our heads around how these weight-sparse models move beyond just, analyzing what a model did,
Right.
to actually training models that are modular and disentangled from the very beginning.
Exactly. And the promise here is, it's massive because this gets right at the heart of the interpretability crisis we've all been stuck in.
The black box problem.
The black box problem. The core issue has always been this phenomenon called superposition in traditional dense models.
Okay.
This is where you have multiple, often totally unrelated concepts that are kind of smeared across the same neurons. They call them polysemantic neurons.
So each neuron is just doing too many jobs at once.
Way too many jobs. And that makes it almost impossible to reliably figure out the mechanism behind any single decision the model makes.
So what's the new approach?
So the solution they're proposing, this weight-sparse paradigm, it's all built on what they call the sparsity bet.
That's a sparsity bet.
Yeah, and the whole approach is to constrain the L0 norm during the optimization process. So you're literally controlling the count of non-zero parameters from the very beginning.
So we're not just cleaning up a mess afterwards. We're forcing the model to be neat from day one.
Precisely. It's a design constraint, not post-training cleanup like, say, pruning. And the result is, well, it's extreme.
How extreme?
We're talking approximately 99.9% of all weights in the transformer are just zeroed out.
Wow.
Yeah. So instead of debugging that giant ball of spaghetti that is a dense model, you're forcing it to build a clean, simple circuit board.
That makes a ton of sense. And for you, the listener, who might be familiar with other methods, let's just be really clear here.
Yeah, good point.
This is fundamentally different from something like mixture of experts, MOE. MOE is, a structure technique. It's designed for scaling.
Right, for speed and size.
This weight sparsity is unstructured, and it's designed for one thing: mechanistic clarity. It's about finding the logic.
It's all about the logic.
So, okay, the theory sounds great. But did they actually find an algorithm a human could understand? Let's get to that aha moment.
The Python single double quote circuit.
That's the one. What did they find?
This is the real payoff. They recovered an exact, verifiable algorithm using only 12 nodes and 9 edges.
That's it. 12 nerds.
That's it. It's incredibly compact and completely clear, and it basically breaks down into 2 steps.
Okay.
Step 1, in layer 0, you have just 2 neurons that act as, quote, detectors and classifiers.
So they spot the quote type.
Yep. And then, in step 2, way down in layer 10, a specific attention head uses that feature to copy the required closing quote to the end of the string.
The idea that a language model can be forced to organize its logic into something that compact is just astounding.
It proves the whole paradigm works. For the same level of performance, circuits from these sparse models were about 16 times smaller than those from dense models. 16 times.
Yeah. The model is demonstrably choosing compact surgical algorithms over these diffuse, smeared-out heuristics.
Okay, but there has to be a catch, right? There's always a catch.
There is, and it's a big one. It's the practical challenge. We have these scientifically elegant models, but they are super inefficient to actually deploy.
Why is that?
Because our current hardware, GPUs, TPUs, it's all optimized for dense matrix multiplication, not this kind of unstructured sparsity.
Wait, so we solved the science but created a massive engineering problem. And isn't adding their solution, this activation bridge, just putting complexity back into the system?
That is the critical question. But
Yeah.
no, the bridge isn't reintroducing complexity. It's more of a necessary translation layer.
A translator.
Think of it like a Rosetta Stone for AI. It's an encoder-decoder that translates the clean, sparse features into the distributed representations that a big, powerful, dense model already understands.
So it's a controlled interface, not another black box. And the utility there is what they call interpretable editing. Precisely. You can go into the small, transparent, sparse model. You can manually tweak a known feature like that, quote, classifier we talked about.
Mm-hmm.
And the bridge then maps that predictable change into the behavior of the giant black box model. It gives you auditable control.
So if we zoom out for a second, what's the big picture here?
Well, the research formalized this idea of the capability interpretability Pareto frontier. It's a bit of a mouthful, but the idea is revolutionary.
Go on.
It suggests that as models get bigger and more capable, they can actually become significantly more interpretable.
That feels completely backward.
It does, but it works, provided they maintain enough sparsity. Interpretability stops being an afterthought and becomes a scalable design objective for safety.
So what does all this mean for you, the person who needs to trust these systems? It seems we have actual proof that we can force AI to show its work.
A necessary path to transparency, for sure.
But the key challenge isn't the scientific discovery anymore, is it? It's the gap between that insight and production reality. The next big hurdle is whether the industry will actually invest in custom hardware for this unstructured sparsity.
That's the billion-dollar question?
The science feels settled. The engineering race has just begun.